This presentation is going to cover the 12-lead interpretation of chamber enlargements and hypertrophies. First, we're going to talk about some chamber enlargements. When we talk about chamber enlargement, we're talking about either dilation of the heart chamber or hypertrophy of the muscle itself. What I mean by chamber enlargement itself, what that means is the chamber does not get any thicker. The chamber just gets larger. So as an example, if you were to look at the left ventricle over here, if this would be considered a normal left ventricle, let's say that's your normal left ventricular wall, enlargement of the chamber just means that the chamber gets bigger, but the thickness of the wall here does not change. Now in a hypertrophy, the difference is that in a hypertrophy, what will happen is the chamber itself might get larger, but also the muscle will typically get thicker. So your distance of muscle here is much thicker. The problem with that, two main problems that you have. First of all, on the outside of the heart, you have this pericardial sac. It's a tough fibrous sac that doesn't really expand all that much. It does have a little bit, but not a whole bunch. The second problem is that you have a decrease in the inner capacity of the chamber itself. So, dilation of a chamber would be an example right here. That would be dilation, which means it just gets bigger, but the muscle doesn't change. Hypertrophy means that the muscle over here does get thicker on this side. So hypertrophy is an enlargement or overgrowth of an organ or a body part due to an increased workload of the muscle, usually caused by chronic pressure on the heart muscle or chronic volume overload. When we talk about chamber hypertrophy, what we're talking about is enlargement of the muscle itself. In this case, you can see here, due to an aortic valvular stenosis, the muscle on this side is much thicker than the muscle over here under the normal heart. Like I said before, another problem that you end up with is you have this really nice chamber over here that has a capacity to hold a lot of blood in the left ventricle. The heart itself, when muscle grows, well, when any muscle grows, it grows in both directions. It doesn't just grow outward or just inward, it grows in both directions, which means your inner capacity to hold blood decreases significantly. This will cause a whole bunch of other mechanisms to kick in to try to increase cardiac output. In this particular case, the cause of the ventricular hypertrophy in this picture was a valvular stenosis, not necessarily a chronic back pressure due to a systemic vascular resistance. The heart muscle itself will increase in size due to the size of the muscle fiber increasing. It doesn't build new fibers. What happens though, the sarcomeres within the muscle do get bigger. This illustration is just a brief review over the muscle fibers and how they contract. This is called the sliding filament theory. If you want to look it up, there are a lot of great videos up on YouTube that explain the sliding filament theory very well. What I want to look at, though, is I want to look at the actual sarcomere themselves. When they say the sarcomeres get bigger, this is considered a sarcomere. It's between the Z lines right here. Chamber dilation occurs when the chamber itself is stretched. Remember, it is a stretching of the chamber. It is not necessarily an enlargement of the tissue itself. The chamber becomes enlarged due to a regurgitation of some kind. The result, though, is that the heart has to work a little bit harder to push out more blood out of the chamber, to push that blood out to prevent congestion of the blood. I don't like to oversimplify the cardiovascular system, but a lot of times I will compare the cardiovascular system to the freeways, or the blood vessels to the freeways. What happens if there is a wreck on a freeway? You end up with traffic congestion. Similar thing can occur if you have too much traffic and there is no wreck, but there's too much traffic. You can have congestion of traffic. Same thing in the bloodstream. If the heart does not have the ability to keep the blood moving like it needs to, there's going to be a backup of blood or a congestion of blood. If it is a failure of the heart to continue forcing the blood through the blood vessel, then it is a congestion caused by heart failure. We commonly call it congestive heart failure. If the heart has to work harder to push all the blood out, and it's during your exercise, for example, it's okay, because when you quit exercising, the heart contractions go down to normal, basically. But what will happen if you have somebody with some kind of cardiovascular disease, the heart will chronically have to work hard to push more blood out of the chamber, which means you're going to end up with somebody who will end up with a congestion of blood due to a failure of the heart, congestive heart failure. So let's go ahead and look at some EKGs, and first we're going to talk about the criteria, but we're going to look at some EKGs to find out what it would look like if we had atrial versus ventricular enlargement. First of all, to look at atrial enlargement, first of all, what you can do is you're going to look at leads 1 and or lead 2 and or lead 3 and or V1. What this means is if you have the criteria to meet left or right atrial enlargement, you don't have to look in all 3 or even 2 of the leads. If you have confirming atrial enlargement in lead 1, then you have it. You don't have to keep looking in all the other leads. Now, if you want to confirm biatrial enlargement, which means the right and the left atrium are both enlarged, same thing. You look in lead 1 and or lead 2 and or lead 3 and or V1. That might seem a little bit confusing right now with all the and ors in there, but as I explain this, hopefully it'll start to make more sense. Let's go ahead and look at the right atrial enlargement. Right atrial enlargement is referred to as P pulmonale, and the criteria for looking in right atrial enlargement is that you, once again, you look at lead 1 and or lead 2 and or lead 3. The reason you're only looking in these 3 leads is because right now we're only looking for a particular P wave pattern. So the first thing that we're going to look at is if you look in leads 1 and or 2 and or 3, and if you have a P wave that is TP, also peaked is another way to say it, and it has to be greater than 2.5 millimeters high. And it's easy to do that. You just use the little millimeter boxes on the 12 lead. So as you can see here, your P wave is starting here at baseline. It is tall and it is peaked, and it is at least or greater than 2.5 millimeters high. Now what's nice about the P wave is you can take a line and see if I can draw it straight here. You can draw a straight line right through, and this is the right atrium. This is the left. Whoops. Left atrium depolarizing. So there's your right atrium and there's your left atrium right here in the middle. The reason that you have this peaking of the P wave here is because the right atrium is going to be enlarged a little bit. So you're going to have a little bit larger of a right atrium than you are a left atrium. So what happens is the signal takes longer to travel through the right atrium, plus it's also larger, which is causing this huge upstroke of this P wave right here. What results in, when it finally gets over here to the left atrium, it has a very sharp downslope because it's coming back to baseline very quickly because it doesn't have to maintain this very large amplitude of electricity due to an enlarged right atrium. Now remember, this peaking of the P wave is greater than 2.5 millimeters, and it is like this, and it is only in leads 1 and or 2 and or 3. In V1, it has a different morphology. So in V1, what's going to happen is you're actually going to have a biphasic P wave. Now, it's usually biphasic anyway, But what will happen is in the biphasic P wave in V1, you're going to have a large initial deflection followed by a small terminal deflection, or scooping you can call it. So once again, you can separate this into right and left halves of right and left atrium here. So there's your line that draw the right versus the left. There's your baseline. This technically is the right atrium, and this is the left atrium. So what happens here is, because like I said before, your right atrium is so much larger than your left atrium, what will happen is in V1 you'll have this huge initial deflection here, this big humping right here, with a very small terminal scooping down here of the left atrium. That is the criteria for the P wave morphology in V1 only in V1. What are some common causes of right atrial enlargement? Some common causes of right atrial enlargement, if you imagine anything that would really cause a backup of fluid into the right atrium, usually consider forward effects. These are going to be COPD, chronic obstructive pulmonary disease. A pulmonary embolism could very easily cause that. Any kind of pulmonary hypertension. Pulmonary hypertension could cause it. Atrial septal defects could cause something like that, especially in younger people. And some structural issues of the heart would be tricuspid or pulmonary valvular disease. Any of these can cause a right atrial enlargement. We're going to go ahead and use this 12 lead here, and like always, we're going to go ahead and start off with our general impression. And our general impression, actually, it does look fast. Calibration, we're going to look at our calibration marker right here. So we're going to say the calibration is standard. Our rhythm interpretation, we're going to start off with our rhythm interpretation. Those are huge P waves, as you can see. And if you look over here, these blue dots on the 12 lead, I got this from, was out of a book actually. And these blue dots here show PACs. So this is actually going to be a sinus tach at, we'll say, 140 to 150 with PACs. R wave progression, you want to look through the precordial leads, and it looks like our R wave progression, there's a late transition, but there is a good R wave progression. Axis, you look at 1 and AVF. 1 and AVF appear to be, looks like it might actually be a right axis deviation. It looks like that this one is up, lead 1 is up. Lead F, this one looks up, but that's a PAC there. It looks like the normal beats, they might actually be below baseline here if I would have to do the counting. So lead F is pointed down, right together, left apart, so we're going to say that this is a left axis deviation. Bundle branch and fascicular blocks, well, we don't have any bundle branch blocks because the P wave is normal, or I'm sorry, the QRS is less than 0.12 seconds. Fascicular blocks, if it's a left axis deviation, it could be a left anterior fascicular block. We look up here in lead 1. It looks like that you need to have a Q1 R3. Doesn't look like I have a Q wave in here. It looks like that that looks like baseline artifact there. So I'm going to say that there's no Q1. We do have an R3, and we do have the up, down, down, and down, but I don't have the Q1 here. So I'm going to go ahead and say no to the fascicular block as well. Now we can start talking about our atrial enlargements. In this case, you want to look over here in leads 1 and or 2 and or 3. So we look over here first, and do I have a P wave that is peaked and it's greater than 3 millimeters, or greater than 2.5 millimeters. If you want to look down here in lead 3, this one goes right across baseline. So I'd say that that P wave is not only peaked, but it looks to be about 6 millimeters. So we easily meet the criteria for that. So let's move over here to our atrial interpretation, and we do have right atrial enlargement in leads, it looks like 2, 3, and AVF. And 2, 3, and AVF. To confirm that, we would have to look over here in V1, and I'm having trouble seeing any P waves over here. I'd have to find out where these P waves are, but I can't really tell over here. So we can't use 1 as a confirming criteria, but we have it in at least one lead in the hexaxial lead, so I know that there is a right atrial enlargement. So let's go ahead and finish interpreting this 12 lead here. So sinus tach at 140 beats per minute with PACs, left axis deviation, and a right atrial enlargement. Now we're going to talk about left atrial enlargement. In left atrial enlargement, just like right atrial enlargement, you want to look in leads 1 and or 2 and or 3 to confirm left atrial enlargement. You're only looking for the P wave since we're only talking about atrial enlargement. Now when we talk about left atrial enlargement, it's commonly referred to as P mitral, or mitrale, I guess, depending on where you're from. To the morphology for something like this, the morphology of the P wave is a little bit more detailed than it is for the right atrial enlargement. First of all, you have to have a total P wave duration that exceeds or is at least 0.12 second. So the EKG on the 12 lead, you're going to have a P wave that goes at least 0.12 second, or 3 little boxes. Also, the P wave has to be notched, or sometimes they'll actually call it humped, like a camel hump. As you can see, you have your camel humps here, your 2 humps right there, and the space between the humps is greater than or equal to 0.04 second. Now this is only going to be in leads 1 and or 2 and or 3, but once again you can take your line and you can draw it right down the middle of the P wave. That is your right atrium depolarizing. This is your left atrium depolarizing. Because you actually have a larger left atrium, what happens is as the depolarization gets over here, it takes longer to depolarize the left atrium. Therefore, what happens is the P wave starts out normal, but then as it gets over to the left atrium, it then is drawn out. And because there's another large piece of tissue there that needs to be depolarized, it basically causes another P wave. That is why you have a very wide P wave that is notched with a space of greater than or equal to 0.04 second between the notches. In V1, you're going to have a little bit different criteria up there. What happens in V1 is you're still going to have your you could have a biphasic P wave. What happens is you're going to have a small initial deflection. Technically, it'll be a small initial positive deflection. With a large negative terminal scooping. So as you can see here, you can draw a line right down the middle right here. This is going to be your right atrium. This is going to be your left atrium. Left atrium. What happens is because you have the larger left atrium, as the depolarization comes over here to the left atrium, it's going to cause a very large terminal scooping. This is only in V1 though. In Remember, in 1 and or 2 and or 3, you're actually going to have a humping or a notching, as it were, of the P wave. Some causes of left atrial enlargement include severe systemic hypertension, aortic or mitral valve disease, restrictive cardiomyopathy, left ventricular heart failure, or anything that obstructs the flow. Now, these are all going to be forward effects that are going to cause problems with the left atrium. Let's go ahead and look at this 12 lead real quick. Whenever we see the general impression, the first thing we consider is it actually doesn't look too bad here. So just by general impression, I'm going to look at it and say that it looks good. My calibration marker is going to be over here. It's kind of cut off, but we'll say that it is standard calibration. My rhythm interpretation, I have a rhythm strip down here on the bottom, so it looks like my P waves are married to all the QRSs. It looks regular, 300, 150, 100, so we'll say sinus rhythm at 100 beats per minute. R wave progression through the precordial leads. As you can see here, it starts negative, continues negative, V3 is negative. V4 is starting to transition positive. It should be a little bit more, but it's not. V5 looks biphasic and V6 looks positive. Late transition, borderline, but I'm still going to say it's a good R wave progression because you start out primarily negative and you end up primarily positive. My axis, we're going to look at 1 in AVF. If you look at lead 1 up here, you actually do have a positive, and if you look at AVF, you have a positive. So that one's positive and that one's positive, so they're both up, so that would make it normal. Normal axis. Bundle branch and fascicular blocks. Well, we don't have a bundle branch block because it looks like all of my QRSs are nice and narrow, less than 0.12 second. So I'm going to say no bundle branch blocks, and I have a normal axis, so I'm going to say no fascicular block automatically. I don't have to look for any other criteria. Now let's look at the atrial. Like I said before, to determine atrial enlargement, you look in 1 and or 2 and or 3 first, and if you have a notching of or a humping of the P wave, but remember the P wave has to be greater than 0.12 second, with the notches have to be greater than, I guess these are both equal to, 0.04 second, and we do meet that criteria over here in lead 2 and in lead 3 and in lead AVF in our what they would call the pulmonary leads. So we have left atrial enlargement in 2, 3, and AVF, and it doesn't look like we can really use this up here as a confirming. We might be able to say that there is more scooping down here, but I think in V2 you can definitely see more scooping. Normally you just look in V1 though, but it looks like in V2 you have this itty-bitty initial deflection with a little bit more of a scooping thing. So we can confirm it up here in the precordial leads. So how would we finish writing out our 12-lead interpretation? It's a sinus rhythm at 100 beats a minute, and we have a good, normal, known, okay, so with left atrial enlargement. Now in a biatrial enlargement, both atria are enlarged. Now what will happen is you'll see atrial enlargement in 1 and or 2 and or 3, and then you'll see atrial enlargement in V1 that is not consistent with the atrial enlargement seen in the limb leads. Let me explain what this means. Let's look at example 1 up here. If you look at example 1, let's say in lead 2 you have signs of right atrial enlargement. So you have a peaked P wave. The height is greater than or equal to 2.5 millimeters, but then you look in V1 and you now see signs of left atrial enlargement due to the larger terminal scooping. Now if you confirmed right atrial enlargement in V1, you would have a large initial deflection with a small terminal scooping, but that's not what we have. So in this case, peaked P waves in the hexaxial leads in 1, 2, or 3, and a large terminal scooping in V1 gives you biatrial enlargement. Now, number 2 here, you want to delete it because I don't get it. I've tried to look at this thing, but how can you have V1 be this and V1 be that? So let's just skip number 2. Number 3, let's say you have signs of P mitral in lead 2. So you have a P wave that is greater than 0.12 second with the humps being greater than or equal to 0.04 second. Supposed to be greater than or equal to. And then you look in the right or in V1 for right atrial enlargement. Now you actually see the large initial scoop or hump with the small terminal scooping. That would be a sign of right atrial enlargement. The book that got this out of, another criterion that you can use to determine right atrial enlargement is look in V6 and your P wave is actually flattened out. So let's look at our 12 lead here. General impression, it looks wide automatically. It looks very wide. Calibration, we can use our calibration markers over here. So we can say that the calibration is standard. Rhythm interpretation, we have a lead 2 down here that we can use, and it looks like it is, let me see our rate. 300, 150, 175. So we'll say sinus rhythm at about, we'll just say 85 beats per minute for fun. And it looks like that this right here is a wide PR interval. So it looks like with a first degree heart block as well. R wave progression, let's look at the precordial leads of the R wave progression. You could say that the R wave progression is actually absent because it starts positive and positive, then it goes to negative, and it stays negative throughout the entire precordial leads. So we're going to say that this is a poor R wave progression. For the axis, you want to look at leads 1 and AVF, and lead 1 is pointed up, lead F is pointed down. So we're going to say that it is a right together, left apart, left axis deviation. For bundle branch blocks, it looks like that we do have a wide QRS here. Now, if we look at V1, we start at the J point and travel backwards, we actually go up. If we had the turn signal method, we would probably be going right here. So let's look to see if we have the rest of the criteria. Do we have an RSR prime? We actually do. There's an RSR prime, R prime prime in V1. In V2, it looks like we have the same thing. Now let's look at our lateral leads. Do we have a slurred out S wave? Well, we don't really have one there. Can't really say we have one there. But we definitely have a slurred out S wave here in V5 and V6. That is a huge slurred out S wave. So we're going to have a right bundle branch block. Now, with a right bundle branch block, very commonly you also want to look for a left anterior fascicular block. We already have the first criterion, which is a left axis deviation. So do we have a Q1 R3? We do not have a Q wave in lead 1. There is no Q wave here. I don't see any kind of R wave in lead 3 right here. That doesn't look like any kind of R wave, so we do not have a fascicular block, although we do have a right bundle with a left axis deviation. Now let's look at our atrial enlargement. Looking at our atrial enlargement, remember we want to first look in lead 1 and or 2 and or 3. We're going to look at our P wave, and it looks like our P wave here is greater than 0.12 second, and it looks like that the humps are greater than 0.04 second wide. So I'm going to say that we definitely have in lead 2, we meet the criteria for left atrial enlargement. So for atrial, I'm going to put left atrial enlargement, at least in lead 2. In V1, it looks like they're kind of biphasic. It's hard to tell if the initial or the terminals are any different. It looks like that you do have that in V2, though. It looks like you have a very small initial with a huge terminal scooping. So I'm going to go ahead and say that we do have a left atrial enlargement. So let's go ahead and finish our 12-lead interpretation. Sinus rhythm at 85 beats a minute with a first-degree heart block. Poor R wave progression. Left axis deviation. Right bundle branch block with left atrial enlargement. When I write this stuff down, I just start here with R wave progression and just work my way through. Poor R wave progression, left axis deviation, right bundle branch block with a left atrial enlargement. That way I don't get confused about and forget writing something because I'm jumping around.